Today I thought I would go over a little more on system identification, and I included a picture at the beginning so you won't forget what I look like. Now this is me in apparently my bathrobe. System identification, it's used frequently, as I say in this opening paragraph. Generally, you're going to mathematically model a system so that you can design the system. Obviously, in an airplane, you don't get to do the cut and try thing where you design the airplane and then take it up and fly it and it crashes and you get to do it again. The same is true for almost any serious engineering system. And non-robotic toys, you're going to have to design the system mathematically, using all the mathematical techniques that we've talked about in this class. And then you're going to build the system, and then there's a high likelihood that you're going to measure it, or you're going to identify it. And this is called system identification, and it's often used industrially. Airplanes, as I say, they're modeled, they're constructed and flown, and then the new plane is characterized. You take it up and you figure out what its model is in a more exact fashion. And so they do this so they can tune their models, and they create high fidelity simulations that they can then use for modifying the plane without having to fly. And so it's useful. Both are used. Never get the impression that everything is just ID'd or everything is just modeled. Both are used. They're used in conjunction with one another, and it makes for a better system overall. So down here in the corner, I've got this picture, a system to be ID'd. I have some test signal and then some measurement that I'm going to make. And test signal candidates in this case, they have to be easy to generate. Obviously, you can't ID the system if you can't identify the system. You need to produce typical results, so results that we understand what they mean, models that we understand, and they also have to have comfortable steady state conditions. In other words, you don't want to crash the airplane while you're trying to ID it, so you can't put in inputs that would cause the end condition to be untenable. And so to kind of think about this, if I'm flying an airplane and I was trying to ID the transfer function, and they do this, literally they do this, trying to identify the transfer function of the roll axis of the airplane. Well, to get the airplane to roll, the primary flight control surface that does that are the ailerons. And so the ailerons you would have to put in an aileron input. And so if you put in a step aileron input, so you just turn the control yoke to 45 degrees or whatever, and hold it there, that's your step input. So you go from 0 to 45, and then the plane is going to start to roll. But the input that you're putting into the airplane is a roll rate, not a roll position. And so as you turn to 45 and hold it there, the plane will eventually start at a constant roll rate. That's really bad because it means that your plane is then falling out of the sky because it doesn't have adequate lift. And so a pure step input is not an option for when I'm identifying that system, because it doesn't leave me in safe steady state conditions. So a lot of times in airplanes, there's a couple of things they approach, but in airplanes, instead of using a step, they will use an input that's called a doublet. And so the doublet looks like this. So you, in thinking in terms of the control yoke, you would turn to some angle, hold it for some period of time, then turn back to the opposite side, and then hold that for the same period of time, and then go back to 0. And if these two are equal, these two steps, then you would be at 0. Now this is called, it has a name, it's called a doublet. And a doublet is just a couple of steps together. Okay, now there are 3 typical families that we use for identifying system. There's sinusoids. One of the things you'll notice about all of these is that you get to all of the frequencies. And if you remember, we talked about Fourier series and Fourier transforms, where we can say that all physically realizable signals can be built out of sinusoids. And steps are frequency rich. They have a lot of harmonic content because of this continuity, and impulses contain all frequencies at a constant amplitude. And so these are the three typical ones I'll use. For sinusoids, I can do one frequency at a time. I can do chirps, or there are other techniques that are available. Steps, I can do unit steps or doublets that we just talked about. Impulses, they have signals that have very high rise and fall times, and so some sort of pulse. Now, these are a little more difficult, although they are used, and we'll talk about that. So for sinusoids, one frequency at a time, what I'm going to do is my system under test, I'm going to put a sine wave at a given frequency, an amplitude. I'm going to measure the output of my system, amplitude and a phase shift. And my gain of my system is going to be the fraction of the two amplitudes. And my phase is going to be how much it's shifted. So I've got my input here, and I shift by some amount phi. And so my dB gain would be 20 log 10 of B over A if I were plotting this on a Bode plot, which is the most typical plot that I'm going to use. And so the procedure here is set the frequency, measure the ratio of B over A, measure the phase angle, plot, and then figure out what the model is. Just as a little aside, if I'm using a system like this where I'm getting a frequency input and frequency output, sometimes a more accurate way of measuring phase is to plot these two signals versus each other. So on an oscilloscope, I would use what are called XY plotting facilities. So instead of plotting against time, I plot the two signals against each other. This is a vector parameterization, and so I've got my X on this axis, my Y on this axis. X would be there, and Y would be there. And the tip of this vector will draw a figure. This is called a Lissajous figure. And for 50 years in science fiction, there would always be something in the background of the film showing a Lissajous figure running on the screen. They can be quite beautiful if you run different frequencies versus each other and everything. They can move, they can do all this stuff. It's quite amazing. But what we're looking for is this nice ellipse, and it turns out that the phase between the two signals is related to the sine of phi is equal to A over B, where A and B are these two amplitudes. And so I can actually figure out of the ellipse, and so I can actually figure out what the phase is. Now this A and B is a bad nomenclature on my part. We'll call it A0 and B0. They're not the same as the A and B there. I apologize for that. One of them is, but the other one isn't necessarily. So I can determine the phase from that, and then I can plot it on a Bode plot, one point at a time. And so I would just go through and determine one, plot the next, plot the next, plot the next, plot the next, and then I would draw my smooth curve, very smooth. And I would do the same for the phase. I would plot all of the phase points and figure out a smooth phase curve. And from that, I can figure out what the model is. And and that, is literally what's done, is you can do this one frequency at a time. Now, a lot of times we don't want to sit there and do 15 frequencies and take 15 phases and that sort of thing. So what I can use in that case is what's called a chirp. And I think I mentioned this before, but a chirp is just a signal that starts at a low frequency and then goes to a high frequency. So the frequency is what is called swept. And by taking the discrete Fourier transform of the input and the discrete Fourier transform of the output, I can get a magnitude and phase, a complete response, everything from this one chirp. And I think I mentioned at one point when we were kind of going through this in a hurry, that pilots will literally take the yoke, say I'm still identifying and they will shake it back and forth in a trained fashion to produce a chirp, and then they will get the measurement, and from the measurement they can get the transfer function, and so they know what the physical model of the airplane is. So that's a couple of ways we do it. The third way that I had listed there, impulses. These are not exactly physically possible, but high rise time, short duration pulses are possible. And what I mean by high rise time is the pulse goes up very fast, comes down very fast, so it's there and gone. Now, the closer I can get this to a true impulse, the closer it comes in the frequency domain to looking flat for all frequencies. So this is an ideal identification device, but it's difficult to generalize. Now, there are a couple of natural impulses. One is lightning. Unfortunately, lightning hits something and destroys it, so the whole identification thing is kind of frustrating. And then there's electromagnetic pulses. You can also do that. An example I have of this from Boeing, this is why it says escape slide story, is at Boeing, the escape slides, when they're explosively deployed. And so in order to test the escape slide, you have to destroy the mechanism for deploying the escape slide. So you knew that one worked, but you don't know the previous one. So that can be a little frustrating. Mechanical impulses, there are hammer strikes that are very close to impulses, mechanical impulses. There are nodal hammers. They measure structural dynamics on airplanes by striking hard points. So they will strike the hard point and then be able to they measure the response of the plane, and from that response they can determine the dynamic model. It turns out that sparks, so if I built like a spark gap and made sparks jump across it, that little crack that you hear as the spark jumps across the gap is an acoustic impulse, a good acoustic impulse. And so a lot of times they'll use spark gap generators to identify a room, the acoustics of the room, what the transfer function of the room. Bose, you may have seen their acoustic stuff, and they're not as highly considered as they once were. But Bose was the first group to take into account the transfer functions of rooms when they built their speakers. And so what they did for the 901, which was considered to be the hottest speaker ever to come out when it came out, they built a typical American living room. So you can kind of think of that, you've got the couch and the television and the stereo speakers and all that kind of stuff. And then they put some high fidelity microphones in the room and a spark gap generator on the other side of the room. And then they pulse the room. And from that, they could determine what frequencies were absorbed, what frequencies were enhanced, and everything. And they designed their speakers based on that. And the speakers sounded amazing for the period. I've since heard other speakers that are even more amazing, but Bose was really wild for a while there. Okay, I wanted to kind of go through a more detailed motor example. And one of these is non-parametric identification, where I really don't care what the parameters are. And so what I want to know is what the gain factor is, what the time constant is, or pole locations if there's multiple poles. And that's all I want to know. I don't want to know the parametric, like the inertias or the damping factors, the torque constant. I don't want to know that. All I want to know is what the overall model is. And in that case, I can ID the physical constants like K and tau, but I don't want to know, or I do not know resistances, inertias, dampers, etc. Now, it's not that I can't know these things. It's just that I need a little more information in order to do that. So I'm going to go through another DC motor ID example. Now you'll say, well, I've got other things besides DC motors. It applies. It's a broad thing. And so once you figure out how to ID it, once you figure out what your test signals are and what your responses are and how to measure those, then you can apply these things to anything. Okay, so I just wrote the equations here. These are just loop equations. I'm going to do something a little weird here, and I'm not going to do it right now, but I go through, you've seen this stuff a million times, but what I'm trying to find is an electrical analog of the mechanical bits of this system. And why I want to do that is because as soon as I can see that, I can figure out an easy way to measure some of the more difficult constants in the system. Okay, and so if I write this equation here, I've got Vn equals I sub m times this equation. Now, one of the things in physics that you can never do is add things that have different units. And so that implies this has got units of impedance or resistance, ohms. That implies this also, this very strange looking thing here, also has to have units of ohms, because I couldn't add it if it didn't. And so if I start manipulating, I'm going to manipulate this into a form that looks somewhat familiar. So I take this term that has to have ohms, and I manipulate it by dividing through by kT squared. And I end up with this, which strangely looks like a parallel resistor formula. Okay, and so if Z1 is a capacitor, then 1 over Z equivalent equals SC equivalent, and I get a C equivalent, an equivalent capacitance. Now this is really interesting because what that says is that the inertia on this is the equivalent of a capacitance. And that inertia is storing energy like a capacitor would store energy. And we talked about flywheels, storing energy in flywheels and that stuff at one point in the class and one time when I was distracted. And the resistor, this damping factor, viscous damping, is the equivalent of a resistor. And so both of them have units of ohms, and I go through kind of a thing that demonstrates that they have units of ohms. The equivalent capacitance has units of farads, and B has units of ohms. This has units of ohms, as it shows here. And so I can write an equivalent model as a circuit model. Now, the first time I did this, I had a need to do this because I was dealing with a non-mechanical engineer who kept sending me emails. This was at Boeing, telling me that motor starting currents could be up to 10 times higher than the running current and everything like that. And it was starting to be really annoying. And so I had to do this to prove to him that it couldn't. And it turns out that the starting current of a motor, the maximum is Vn over R sub A. And that's initially the capacitor is a short, so this has no effect. The motor isn't turning yet. That makes sense because it's not spinning. This is viscous damping that's caused by dragging air around. And so that said, that's the maximum starting current from stop. Now, a full reversal is, in the case of a full reversal, this capacitor would be charged. Essentially, if you'd put in minus Vn and caused the motor to spin completely backwards, and then switched it to plus Vn, then this capacitor is charged. It has to lose its charge, and so your starting current, I just put Imax here. Your starting current is approximately 2 times Imax for a reversal. So if anybody ever starts telling you that starting currents can be huge and stuff like that, they're limited. They can only be so much bigger. They can't be massively bigger. This model makes it easy to see how to measure the viscous damping. And then using the transfer function and find KT and J. This is kind of an alternative to what I talked about last time. So this is a gain factor and time constant given the motor model that we used before. And I realize I'm pointing at my iPad and not circling things, and I apologize to you. I'll try to get better. So measuring the parameters, I can measure R sub A with an ohm meter. We talked about that last time. I can measure this torque, and I can indirectly measure this B by letting the motor run at a steady state and then looked at the steady state equivalent circuit. And so by doing that, what I'm doing in that case is I have to be able to measure I sub m. So I'd have to measure the current in the motor at steady state. I know what the V sub n is because I applied it. I've measured this and I've measured that, and so I can calculate B directly, so I would know what the viscous damping factor was. And then as soon as I've got that, the gain factor of the motor can be solved by solving that, and I have the entire motor model at that point. I can get J from the rest of the parameters at that point and the tau, and I've characterized the motor completely by doing this. System identification is a useful skill. At some point during a design process, you are going to identify a system. You're going to put in some test signal, like a step. You're going to observe the output and figure out what the transfer function of the system is. Again, don't think this is a replacement for mathematical modeling of a system. It is not. However, it is an aid, and it is a companion to mathematical modeling. And so being skilled in both is very useful. I will post a discussion on this if you've got comments or anything. I'm going to try to go through everything that we put up on the board that one day, talking about various things, and I should post another one of these soon. If you've got comments or anything, first of all, be nice. Second of all, you can tell me things without being vicious. But if you got comments or anything, please tell me, and I will try to incorporate them. I know this is less than ideal, and I much prefer being in a class with you. But right now, they will not even let me. So I will see you next time. Thanks.